All right, welcome back to the next speaker in the session. Our next speaker is Anand Subramoney from the University of Bochum. And now, after all the biological plausibility, he is going to take it out again to see what can be done with spiking neural networks if you really optimize it for neuromorphic hardware. So his title is Beyond Biologically Plausible Spiking Networks for Neuromorphic Computing. I'm looking forward to your talk, Anand. Thanks.
Thank you, Freeman. Yeah, hi everyone. So as Freeman introduced, I'm Anand. I'm a postdoc in the Institute for Neural Computation at University of Bochum. And today I will talk about how we can do better than spiking neural networks for neuromorphic computing. Okay, so the spiking neural networks that we all know and love were developed as models of biological neurons with different levels of details, right? So there were like point neuron models, there are more complex multi-compartmental models, and they've become like the canonical model for neuromorphic computing today, both for digital and analog neuromorphic computing. But the focus of neuromorphic devices is shifting further towards deep learning applications with higher expectations of task performance, but also energy efficiency. And I think we need to ask ourselves, are these biologically inspired spiking neural networks really optimal for deep learning with neuromorphic devices? Or can we do better by really customizing things for specific applications and specific neuromorphic devices? And so I contend that we need to design deep learning architectures from first principles for deep learning on neuromorphic devices by really distilling the essential advantageous properties of these biological models and using them to design our architectures. Right? So now the obvious question is, what are these essential properties of spiking neural networks that we've been using all this time? Or in other words, what is the desiderata for neuromorphic architectures? And so one obvious one is sparsity, so which can be both in time and in space. So the sparsity in time is activity sparsity, where activity is transmitted only when needed. So this kind of corresponds to the spiking of spiking neural networks. And then there is parameter sparsity, which is just reducing the number of parameters. So activity is only transmitted to the units that need them. So the second key property is event-based communication, where communication only happens between different units through discrete messages. And so the interesting thing is when you combine event-based communication with activity sparsity, depending upon your dynamics, you can actually have units that only need to update their state on incoming events. And this can save a lot of computation and really provide a lot of efficiency to the model. So there are, of course, a lot of other properties of spiking neural networks that we use. Asynchrony, that is not having a shared clock signal, and maybe some other properties that I've not really thought of. But in this talk, I'm going to focus on just sparsity and event-based communication and try to design an architecture that can use this and do well. So just to kind of continue this point a little bit, so you can really think of a general purpose event-based model where you have an event generating mechanism for each unit and have arbitrary event dynamics. So the core property is that you have an internal state and some thresholding which decides when to emit events. And the dynamics can be based on leaky integrate infer neurons or adaptive exponential, which is like the standard models. And in these models, the internal state is the membrane potential of the neuron. But then the internal dynamics could also be based on LSTM and GRU with the threshold applied on their internal state. Right? Or you could use any arbitrary dynamics for this model and add a thresholding event generating mechanism, and you could use it for the appropriate application. So to actually apply this, so we have worked on using the gated recurrent unit to develop such a model. And so this is based on the archive paper where I put up a link right here. And so the gated recurrent unit is something that works really, really well for deep learning. It's a very performant recurrent architecture. It's also quite simple. And if you're not already familiar with it, this is kind of what it looks like. So there is an update gate that is that's a gate that takes depends on the external input and the recurrent state. There's something called a reset gate. So this is a bit different from a spiking neural network reset, but just using the terminology of the original GRU paper. So this is also a gate based on the external input and the recurrent state. And then so the update gate kind of determines how much of the new input comes into the cell state and hence the output. And the reset gate kind of determines how much of the input previous recurrent state is kind of reset or deleted or forgotten in some way into the final output. So we add a event generating mechanism to these dynamics, and you essentially end up with what we call the event-based gated recurrent unit. So the event generating mechanism is essentially a Heaviside step function with a threshold. So you take the internal state, subtract the threshold, and if it's above zero, then you emit the event. So the major difference from a spiking network is that the event that is emitted contains information about the cell state. So, and if for a discrete time simulation, this is actually like a real valued number and not binary. Right? And the cell state dynamics is exactly the same, almost exactly the same as a gated recurrent unit, but there is an additional term which corresponds to the spiking neural network reset, because we don't want a unit to be sending events in consecutive time steps just because it went over the threshold once. So this is the event-based gated recurrent unit that we have been working on. And so the learning in this model, so we do have this non-differentiable thresholding function, and we can use a pseudo derivative, just like a spiking model, for doing backpropagation through time. And so if you notice, there's an interesting property that in general these event-based models have, which is that you can choose a pseudo derivative in a way that backpropagation through time can be sparse. So the backward pass can be sparse. So here in this figure, you kind of see, so in the forward pass, if there are these two units and they're active at like only specific times, so obviously like the forward pass only goes through the active units. And with this particular choice of a pseudo derivative, which is this piecewise linear function, which is zero everywhere except for this small region, the backward pass is sparse as well, because the gradient is zero for all the time steps and units where we are outside the support of this pseudo derivative, right? So, or the surrogate gradient. So we only need to backpropagate through the units that were active and some units that were not active but had an internal state within this region. So essentially, not only is the forward pass sparse, but the backward pass is sparse as well, which provides a huge advantage in terms of efficiency, as you can imagine. Okay, so we essentially use this event-based GRU and tested it on a bunch of tasks. So the first one we tested this on was this dynamic vision sensor gesture recognition task. So if you're not already familiar with it, it uses this dynamic vision sensor, which generates events based on movement. And this is an example of a data point where a person is waving their arm over here, which is the gesture. And this is converted by the DVS camera into like a sequence of events, on and off events over time. And so with our EGRU, what we essentially show is that we can beat all the models, including non-spiking models. So we didn't really compare it with spiking models because they're quite far behind for this particular task. And so there are a couple of ways that we measure efficiency. So one is, so there's obviously the sparsity, activity sparsity, where we kind of look at how many units are active on average. And as you can see, our EGRE model is quite sparse. So we get like something between 76 to 83% activity sparsity. And this is for the forward pass. And we can also look at the backward pass sparsity. And depending upon the architecture, it's usually less than the forward pass sparsity, but it varies from about 46 to 72%. But to kind of encapsulate the forward pass sparsity in a useful number, we calculated what we called effective MAC operations, so multiply and accumulate operations, because this is one thing that is quite important for certain classes of neuromorphic devices. And this is essentially the number of operations that we would need to do because of this forward sparsity. So the number of operations that leads to a reduction because of the forward sparsity. And so what we see over here is that with quite efficient models, so there are like essentially three variants of a model: with and without a convolutional network, and with and without data augmentation. And so the best performing model with an LSTM uses a convolutional network and data augmentation. And we're able to beat this model with a convolutional network and data augmentation, but with a fraction of the MAC operations compared to the LSTM model. But then we can actually further reduce it if you're willing to put up with a drop in the performance and have a really, really efficient model that reaches about 88% test accuracy. Okay. And this is kind of an example of what the activity of this model looks like. So it's really, really sparse, and it's kind of reminiscent of spiking networks, right? And this is exactly what we want to achieve. Okay, so similarly, we also tested this on sequential MNIST classification. And if you're not already familiar, this is a task where you take an image and input the pixels of the image, pixel by pixel, to the recurrent network, and ask the network to classify the image. And again, over here, we see that, so we are not beating state of the art, but we get pretty close to state of the art with non-spiking or non-event based models, but with a fraction of the multiply accumulate operations, right? Which implies that there is like really high activity sparsity and overall fewer operations. And the other interesting property that we can look at from this particular example is that we can look at the scaling. And this is a plot where on one axis you see the performance of the model in terms of the number of epochs to convergence, and on the other axis you see the total amount of computation required for that model. And the x-axis is the size of the model. So the point over here is that as you increase the size of the model converges faster, and that's kind of what you would expect. But the total amount of computation doesn't really increase on the same level. So if you notice, the x-axis is logarithmic scale. So the total amount of computation about doubles when you increase the size of the model by about 10 times. Right? So we're able to kind of keep this efficiency because of this intrinsic sparsity of the model. And finally, so the larger task that we looked at was language modeling. So we tested this on PenTreeBank and Wikitext2, and we get perplexity very close to state-of-the-art networks based on LSTMs, but with a much lower kind of computational footprint, both for the forward pass and for the backward pass. And over here, you can kind of see the effect of the width of the support of this surrogate gradient or pseudo derivative, and you can kind of vary this to control the backward sparsity. So you can make it more narrow to have higher backward sparsity with some loss in performance, or make it more wide to get a bit of higher performance. But there is kind of a sweet spot in between where the performance is good, and the backward sparsity is not so bad. And this is kind of like a tunable parameter. Okay, so very quickly, so one of the reasons that we chose the GRU for this event-based model is that it has this very interesting property that you can write it in continuous time, just like many of the LIF models or ALIF models, because the GRU equations are essentially forward Euler equations of a continuous time model. And so once you have the continuous time model, we can analyze this and even derive event-based gradient descent updates based on this model. So this is kind of the overall description of the model, and you can formally describe the events as changes in the state, the values of the state before and after. And the activations also are defined in terms of the events that occur. And so I'm not going to go into this in too much detail, but essentially the bottom line is that you can derive a event-based gradient update where you only need the values of the backward adjoint variables and the forward variables at the times of the events, and you can use this to calculate the weight updates, right? So which can lead to very efficient backward pass. So this is kind of very similar to the event prop algorithm described for spiking neural networks. Okay, so in summary, biologically plausible spiking neuron dynamics are suboptimal for deep learning on neuromorphic hardware. So we can modify any unit dynamics to make it spiking by adding an event generating thresholding function. And I've shown a specific instance of using the gated recurrent unit and making it event-based in an architecture called the EGRU. So this EGRU exhibits very high activity sparsity as well as sparse learning updates, and it can be written in a continuous time form that supports event-based gradient descent updates, and you can do rigorous mathematical analysis. So for example, you can look at whether it has a vanishing gradient problem or not, and so on. And it can potentially replace spiking neural networks for challenging and complex tasks on neuromorphic hardware. So very quickly, the outlook for this is we also plan to explore other unit dynamics that are appropriate to different use cases based on the architectures that are known to work well, but also a good fit for specific neuromorphic devices based on the features that the neuromorphic devices offer. So for example, you could have non-binary packets for communication. You could also have more efficient software implementations of these general event-based models that are efficient on CPUs and GPUs and conventional hardware to some extent. And we're currently working on implementing this EGRU model on Spinnaker 2 and scale it up to way more parameters and units as the Spinnaker 2 allows. So this is joint work with these people from TU Dresden, from Khalil, Mark, and Christian, and David from Rube as well. And our archive paper is linked over here. Thank you very much.
Thank you very much for this nice talk. So maybe I can quickly start with a quick question. I think it was the performance table on the DBS 128 gesture. And one thing I was wondering is if you still have it. So it seems like you compared the EGRU with data augmentation and CNNs to an LSTM didn't have the CNN part and no data augmentation. So I was wondering, could you comment on that? Shouldn't be the CNN GRU the right plus data augmentation be the right comparison to really?
Yes. Yeah, that's right. I mean, so we wanted to compare with like the best performing non-spiking architecture. So the CNN plus GRU doesn't do as well as the LSTM, at least in kind of reported literature. So which is why we compare it with the LSTM, right? But you're right that yeah, I mean like a proper kind of equal type of model comparison would be a CNN plus GRU plus data augmentation.
Right. So then Tim Muscovy has a question. So do you think it's worth exploring events with different magnitudes, for instance, coded on a few bits rather than all or none events, spikes?
Yeah, so that's, I mean, so I'm just going to share my PowerPoint again and just to kind of, so I didn't realize the sharing was stopped. Yeah, so that is definitely an option. So I think it really depends on what the underlying substrate is that we want to implement it on. So theoretically, of course, like many of these things are quite similar, and the learning updates and like all the analysis is going to be quite similar irrespective of the type of the event. So I mean, we don't actually like plan to explore right now these kind of events, but it's definitely a possibility. There's nothing to speak of against it.
Okay, last quick question is by Ezekiel Williams. Perhaps I missed this, but I'm curious if there was a quantitative argument made for why standard biological model neurons are suboptimal for deep learning on neuromorphic hardware.
So there is, I mean, in this talk, I didn't really have like quantitative results or direct comparisons, but essentially in many of these tasks, spiking neural networks don't even come close to this level of performance of non-spiking networks. And secondly, there is also like a lot of issues. I mean, so I spent like a lot of years working with spiking neural networks, so it's not coming into this as an outsider. But there are a lot of issues in terms of like having long short-term memory, for example, in terms of having trainability, in terms of having rich enough dynamics to model like really complex and difficult tasks. And this is essentially what this is solving. So we're taking models from deep learning that we know work for these complex tasks, but make them event-based so that they can run efficiently on neuromorphic hardware. So that's kind of the idea.
Okay, thank you very much. There are more questions actually now in the last minutes, a couple of more emerged. Unfortunately, to stay on schedule, we'll move on now. Please feel free. I'll just invite them. I hope that's fine, Anand. I'll just invite people who didn't get their question asked to just write to Anand to reach out if you're interested in getting answers. So thank you again very much for this presentation. And we'll see each other again in a couple of seconds in the next session.
Thank you very much.